before we start on the actual topic of today, that is recursive algorithms, I want to do a little bit of review of discrete math 1 on what we did on algorithms, also what pseudocode and complexity, all these terms are going to come back. It's a quick review. So this is basically all from chapter 3. So this is in chapter 3 you find all this information. So I strongly suggest to go back, look there, exactly what goes on. And rather than giving a general overview, I'm just going to work out on one example and then touch on all these topics. And I want to discuss the so-called insertion sort. And so the insertion sort, so what we are looking for are algorithms that sort a list. So that it's the sorting, and that we have seen in, if you remember this, especially in discrete math 1, is that once a list is sorted, many other operations can be done much easier on there. For instance, searching for a term in that database, comparing, you can calculate things much better. So sorted lists are always the list. Every big database, like if Google has to makes these huge search bases, they're all sorted so that you can quickly search through it. The sorting itself is time consuming sometimes, but once it's carried out, all the other operations that you need to do are much quicker then. So sorting is a very important algorithm, and it's almost every database program, every program that deals with databases is going to do that right from the bat, sorting things. And so the insertion sort was a sort. So let's see. We have a certain list. Let's call this. I'm going to take a. Let me do it this way. An alphabetic list, and we want to sort this. So what is the sorting algorithm? The insertion sort algorithm does. It says, okay. Of course, when I say sort these letters, I always mean alphabetically. Okay. It takes. Of course, it starts with kind of not doing anything and initiates itself. That we'll see all the time, and especially when we do these recursive algorithms. So where a recursive algorithm, I'll say more about it in the next video, is an algorithm that reduces the calculation to a smaller or a previous calculation. Okay, like the recursive definition of a function, define a function on the previous values. Okay, so we start here with saying, okay, we start, to the left is my sorted list on my line, and to the right is the thing that is not sorted yet. So of course, when I have only one element that is clearly sorted. So the next thing the algorithm does is it picks the first element, so in the unsorted part, and then compares this. Where does it go, there or does it go there? It asks. Okay, so it has to do one comparison. And so this gives me, of course in this case it would be D and Q, right? And so let me put green is the okay, let me be a little bit more consistent with my colors here. Sorry, I'll do it over again. So Q, green will mean the list that has already been sorted, and then, so what we have now is, and after one step we are there. And then the next thing the algorithm does is says, okay, now I look at the first element in my unsorted part, and I'm going to see where does it fit. So there are three positions. Is it here, or is it there? And each time it compares itself. So first it compares itself with D, and it sees it before there, so it actually stops there. But in principle, it has to go through all this. So, okay, let me, I think I chose my list a little bit carelessly. Let me make it a little bit nicer list, a little bit more action-packed list. Okay, so let's do this one. So, okay, so the next thing, A, goes all the way in front. So we have A, D, Q, and what is left then is X and Y. So the next step in our algorithm is you take this X, and then you say, where does it go? Is it less than A? No, it is not. Is it less than D? No, it's not. Is it less than Q? No, it's not. So it goes all the way there. So we get, this was in green, right? A, D, Q, X, and then left is I. This is I, okay? And then the last one, now we ask, where does I go? Does it go there? No, it's not less than A, it's not less than D, but it is less than Q. So here we go. So we'll go in there. And so we get the number is A, the list is A, D, I, Q, X, sorted. And so what do we do? Let's calculate also the number of steps kind of involved, okay? In the first step, well, we basically put Q in my first list, okay? And then I took this D here, and I compared it with Q. So this is basically one comparison, okay? So let me put it that's one comparison here. So the number of comparisons. And basically, that's the only thing the algorithm does, comparing, and then puts it somewhere, but that, remember, these little things are not considered really as steps. It's how many times you carry out a certain, how many times you carry out the core of the subroutine, the core program, okay? So, okay, there's one comparison. Now, when I have A, I have to compare actually with the new list. The green list now consists of 2 elements, so there are 2 elements I have to compare with. So here I have 2 comparisons, okay, with this A. For X, now they have to compare with A, D, and Q with 3 elements. And then for I, finally, I have to compare with 4 elements. So we see that the total, we have somehow 10 comparisons that we need here. Okay, now, so we could ask, what is this in general? Suppose we have a list of length n. So here the n was 5, so here was n5, right? But in general, this list could be much, much longer. And of course, it's not just going to be letters. Most likely, it's going to be terms, words, something like that. Social security numbers, could be anything, right? So we have a list of length n. So how many if you do this in general, so how many comparisons for a list of length n? So this was n is 5, and this is n general. Well, it's the same thing, right? The first time you have to compare with 1, then with 2, then with 3, then with 4, and all the way up to, well, it seems we do only the previous, before you have the final list, you have a list with length n minus 1, right? And then your last letter, or the last element has now to be compared with the n minus 1 that you have already sorted. So it goes all the way up to n minus 1. Now, so we have to add this all up, and this is the sum of the first n minus 1 elements, but that is not so hard to see that is actually, there's a formula, right? I have to think about this, so this normally it's with n. So it's n squared minus n divided by 2. Let's see, is this correct? So for f5, 25 minus 5 is 20, divided by 2 is 10. Yeah, this gives me this number. But this is too much detail. So in the big O notation, well, let me put it here, the big O of this, we say, what is really mattering? What is this here? Well, okay, there's a quadratic in there with a coefficient. So if you would write this out as a polynomial, it would be 1/2 n squared minus 1/2 n. First of all, in the big O, these constants do not matter, so we ignore them. So okay, in the big O, I'm going to the big O, and in the big O, I'm going to say, what are the things I'm ignoring? I'm ignoring this because that's just a constant factor, okay? What I also ignore in a big O calculation is everything that is small, or smaller than anything, than another thing. This n, because it's degree 1, is smaller than degree 2. So also all this is gone. So the only thing that is left is n squared, and so this is O n squared. So this is what we call quadratic complexity, okay? Which is not great, because if you're doing with a list of, say, 1,000,000 elements, which is a very reasonable list if you're doing some big data, well, it's actually rather small even then, but 1,000,000 square, that's already quite a lot, okay? 1,000,000, that's easy, computers can easily handle it. 1 billion, now you're getting already a little bit, so squaring, this is not the best algorithm, the insertion sort. Now, so this is an algorithm. I talked about the complexity of algorithm, but now I should also discuss how we implement that in how we code that. But we don't use actual program language, but we use what is called pseudo-code. And again, go review this from last time. It's in the back of the book. There's a discussion of the pseudo-code. And so the procedure here that we are doing, okay, so now I have to decide on, so in the textbook they use boldface to indicate pseudocode terms, commands. Okay, so how can I do this here? If I do this pens, they're gonna be. Sorry, I should have thought about it before I did this, but okay, I'm gonna do. So we have procedure. So okay, I hope it somehow stays legible. So this is a command, right? Procedure. Then we give it a name. The procedure name is. This is gonna be very insertion sort. And it depends. It consists of a list of elements that can be compared. This could be real numbers but it could also be words that can be compared alphabetically, or some other things that can be compared. Okay, so I'm not going to be precise very much, and of course n is the length of the list. Okay. So what we do? Remember these are gonna be. So this is gonna be. Okay, let me get a little bit rid of my coloring here. Okay, oh shit, that was a D, right? So this is A1, this is A2, this is A3, this is A4, and this is A5. Okay, and we start with the second element already, right? With D. So that is what. Let me put it this way: 4. And then I'll go as start with the second element, and then take the third, and then the fourth, and the fifth. So in other words, I go through the black list and try to put these into the green, make them correct. Okay. So this is my counter, which I call J here. So this will be J equal. Oh, sorry, this should have been in the other. So my counter is J equals 2 here. Here J will be 3, the third element. This will be the fourth element, and this will be the fifth element that I will. Okay. So for J, going from 2 to N to, I'm sorry, this is gonna take a little time, as I said, by doing this, but to N. Okay, what do we do now? Well, you compare it to. You're gonna now. The next thing you do is go through this list, through the green list, okay? And you take your element and compare it. Let's look somewhere at what happens at stage 4, for instance, right? It's when you analyze an algorithm, you should always look somewhere in the middle. What is going on in general? If you look at the two beginning steps, then you don't see enough things happen. But let's look at what happens in this case here. Well. So J is 4, and what I'm doing? I'm going to go to the green list. So I have to have a counter that also tells me where I am in this list, and this counter I will call I. So I will be 1, 2, 3 in this case, because of 3 cases, right? This will be the first element, the second element, the third element. Okay. And by the way, so when A1, A2, A3, A4, A5 always refer to the positions, right? So this is now originally Q was A1, but now Q has become A3. So we keep renaming our elements because we want in the end A1, A2, A3, A4, A5 to be in order. Okay. So I'm going to compare X with A1. With A1, with A2, and with A3. So okay, how does that work? Okay, so I start with I equals 1. See, each time I indent means there is this is now inside this for loop, right? So I is 1. I'm getting to the first position of my green list, and then I compare. What I'm going to do is I'm going to walk through this list and compare this element. Which element is this? This blue element that I circled, the one that I'm going to try to insert, that is element given by this index, right? So this is AJ. Okay, so this is what while AJ, remember that's the one that I'm trying to insert. If this is bigger than AI, remember the I is the index that goes in the green list. As long as my AJ is bigger than the elements that I'm comparing it with, I know I have to keep going. I have to go to the next and then to the next and to the next, okay? So while this is true, what I have to do? Well, then I have to increase I, as I said, we have to keep going. I'm going to check it now with the next, okay? So originally I was 1, and I compared x with a, and it's no, so that's not true. So my while loop is still in action, still is valid. So I increase my I is now 2, and now I'm comparing this. Now I do a comparison. J is always fixed, right? It's the A that I is the ones that are walked through my green list. So I'm comparing it, sorry, this green list. So I'm comparing it with the second element, no. So increase again, I come with third element, no, increase again. So what is it then that the result is? So when I jump out of the while list, I know that this is, that, let me write this up, what do we do? So I now know where this element belongs. It has to go, when the while this stop, I have to put it in. So, and this is a little bit technical here, and I'm just going to write it down, but this is no longer really what happens. This is just saying, okay, now I have to, in the green list, you have to insert it in that position. But that's not really the search anymore. We don't do any comparisons anymore. So let me write down what it is. So this is, yeah, it's a M, so 4 K going from 0, and I'll explain why 0 here, oh no, here, to j minus I minus 1, aj minus k is aj minus k minus 1, and then ai is m. So I repeat. Let's see what happens. I'm not going to do the details of this last part here because that's no longer important. So as long as in this loop, I have to keep going. So I keep increasing my index. Okay. Once I have, when this I'm done, of course, and this also is done when the worst case that could happen is that I'm work to my whole existing list and didn't find anything yet. That means this happens exactly in this case, I guess, right? Because I go to 1, 2, 3, but I haven't found anything. So at this point, I jump out, and I know now that the ith element should be the new. This new element should be on the ith position. But I cannot do that right away. So that is why I temporarily store this in a memory variable m. And then this part, what does this do? It just shifts everything, all the elements that are behind it. It shifts them. Wait, what is it? It shifts all the elements. Yes, all the elements. It shifts them all up, so that I have a spot to put my this element in there. Okay, so for instance, in the last step here, what happens is, let's see when this you see here, I said we this is when this stops, right? So at this point, what I'm going to have to do is, this will be A1 still, this will be A2, this number will now become the A3. So I have stopped at position 3. So that is here the AI has to be now the last element that I dealt with, that was AJ. Okay. And what has to happen with these two guys? Well, they become no longer the third and the fourth element, they become the fourth and the fifth element. So I have to move them up a little bit, and that is exactly what happens in this little loop here. I'm not going to go to the details of it, so you can check it yourself. Okay. And so this is an example of how an algorithm, how do we write down algorithms in pseudocode. And so this algorithm then eventually, when it finishes everything, the output will be, so this is sometimes we can add this, you remember, we add comments in this way by braces. So A1, AN is now sorted, is in increasing order. Okay, so that's the objective of this algorithm. Okay, so let's leave it here. Go look at the other stuff more details in chapter 3, and then I will now discuss how we apply this to the recursive algorithms.